So I'll be talking about semantic Wikipedia networks. So I'm a computational linguist too, but my approach is a little bit different. So I first built a knowledge representation, and then I do stuff with it. So in a nutshell, whichever natural language task, language-related AI thing you want to do, the main problem is that you need a lot of knowledge. So you guys, when you understand language, you process it, you reason about it, you use millions of facts about the language or just background knowledge about what words mean or how they're connected in the world. So you don't actually notice this, but there has been estimates that you use around 80 million facts a day. Okay? And that's quite a big problem. So if you want to represent this knowledge so that we can do some AI with it, you need to represent it and learn this stuff automatically somehow. So the semantic Wikipedia networks that I'm going to introduce are a sort of knowledge representation. And as you can see, they're going to have a bit of a network form. So we've got things, concepts, which are going to be the main nodes, and then you've got relations between them. They are based on Wikipedia. So I use Wikipedia text to generate these networks. And they're semantic in the sense that they tell us something about the meaning of these words. So the talk is going to have 3 parts to it. I'm first going to give you a little introduction on what sort of knowledge you actually need, or why it's so difficult. Then I'm going to tell you how about these semantic Wikipedia networks. And then I'm going to show you an application which is going to be semantic relatedness, and you're going to see some similarities with what Manish has been talking about. So, introduction to knowledge. Let's look at some very basic thing that you do with language every day. It's called co-reference resolution. So, say I give you the sentence, I saw a piano, and then I go on saying something like, the beautiful instrument, and then something, whatever. So for you, you're going to be able to notice that this and the beautiful instrument refer to the same thing in the discourse, right? And you're not even going to think about this. It's not a hard thing to do. And the reason why you can do this is that you know that a piano is an instrument, right? Very simple. Now let's imagine another scenario, more in the area of AI. You want to build a agent that can go off onto the internet and do something for you. So for example, you tell him, I want to buy a grand piano, roughly this sort of range of price, and these brands, and it can go off and search the internet for you, look at all the websites, and retrieve the information and present it to you so that you don't have to do it. This is kind of the vision of semantic web. Well, that's heard about it. So let's say it comes across a website that says all instruments are on sale. And so it's going to know, oh right, so also the grand piano is going to be on sale. Exactly the same information that it is a subtype of an instrument. Now there are knowledge representations that do this, so that give you exactly this taxonomic information. The one that is most widely used is called WordNet. It's also used for lots of other computational linguistics tasks, but really what it gives you is you're going to have the grand piano concept somewhere here. By the way, can you read it when I write down here? Yeah, okay. And then it's going to tell you that this is a keyboard instrument, and there are some other subcategories, and you're going to come to the instrument, and then all the way up somewhere there's object or entity. Similarly, you would have string instrument here and violin down there. So that's pretty cool. So with this knowledge base, we can already do this sort of reasoning and deal with these tasks. But taxonomic knowledge as such is not going to get you very far. I mean, it's going to solve a few problems, but not all. So another example is, say you're going to do machine translation. and I give you a German sentence with a word that has two meanings, right? And you have to choose which one is correct in the translation. So what you get is, I played on the either wing or grand piano. So we've looked up the German word Flügel in the dictionary. We know that it can mean these two things, and now we've got to pick which one is correct. I mean, it's really obvious to you, right? But if you type it into Google Translate, it's going to get the wrong one. It's going to tell you it's a wing, and that's because it's the most frequent sense of the word. So the kind of knowledge that you would need here is to say, okay, the relation played on, so something that play on as a relation, takes the domain person, and you'd be able to say, okay, yeah, that makes sense, that's a person, hopefully, and range, instrument. And if you have this sort of knowledge, you can start solving this. Now, there are frameworks for knowledge representations that would have this sort of stuff. They're called ontologies. They have the nice properties that you can reason on them logically, right? They're really nice, but they have two drawbacks. First of all, they're, again, pretty limited in what sort of knowledge you can actually put into them, while still being, like, it's still quite a big fight to reason efficiently on them, right? So, okay, now we've got an idea what sort of knowledge we maybe want, and we also know that this is quite restricted. But the real problem with all of this is that even if we know what sort of knowledge we want to have and how to present it and how to reason on it, it's this sheer amount of millions of facts that we really want to represent. And we somehow have to create these knowledge bases. So to give you an idea, WordNet, the taxonomy that we just had, covers about 150,000 concepts. Which I don't know whether it sounds like a lot or not. It's quite nice, it's got quite a lot of common English words. To give you an idea, the current number of articles in Wikipedia is 3.5 million. Right? So this is pretty restricted in what sort of concepts or things you can actually talk about. However, it took 10 years to build by experts. So that's the big problem we run into.
It's a completely manual thing, these ontologies they're made?
Pretty much. So I mean, there are advances to learn the stuff, or like learn these is a relationships statistically, for example, so that is there. But you always have this trade-off of precision if you have experts doing it, or some automatic process. Really the ones that are used, or WordNet and ontologies, are primarily manually built by engineers.
That's why it took so long.
Exactly, that's it. So this is the big problem. So obviously what we want to do is say, so how can we somehow do this stuff automatically? So what you want to do is learn from text. But you'll be able to see that this is a chicken and egg problem, right? If we could, so we need the knowledge base to understand the text, but we need the text to feed the knowledge base. Right? So we don't know what to do with it. And this is called the knowledge gap in artificial intelligence. And it's really a pretty big problem. And no one really knows how to solve it. So let's take a step into acquiring knowledge bases automatically. So I want to think for a second why Wikipedia is such a good resource just for us, right? I mean, we all use it daily. So what are the things that really make it such a good resource? The first thing is that it has really pretty broad coverage. I'm pretty sure that like, most things you in daily life want to look up, you'll find an article about, right? And even in pretty specialized, our fields, our research fields, you'll find an article about it. So that's pretty good. Secondly, there are encyclopedic articles. So you kind of know that everything you're going to read is like a short introduction, it's all relevant information, it's not going to wander off telling you stuff that you don't want to know.
So it has some structure.
Exactly. It's an encyclopedia. Apart from that, if you just had a look at text that contained the words in your Google results, you're going to get more irrelevant text than if you have a look at Wikipedia directly. Next thing is really up to date. And it's also growing really quickly. So right now there are about 3.5 million articles. In 2006 there were 1.5. So because everyone engineers it, or it's like a collaborative effort, it manages to do that. Compared to Brockhaus, which as soon as it comes out, is already out of date. Is this just a German thing, or is it normal encyclopedia? Yeah. Is it a German thing? Okay. It's a bit encyclopedia, right? Next thing is that there is some meta structure to it. So for example, you've got these info boxes. So whichever country you look up, you're going to get the same style of info box that's going to tell you, population, etc., etc. So you already have quite a nice structure and overview and things that you need. You also have the category structure. So if you scroll to the end of the Wikipedia page, it's going to give you, this is a type of, apple is a type of fruit, and you can click on fruit and see what's going on there. And what we also have is hyperlinks. And these are really convenient because we don't have to search for an article ourselves. It's usually stuff that is really relevant, etc. So this is really quite helpful. Now obviously Wikipedia is human understandable. It's not computer understandable. We can't do any sort of reasoning with it yet. But if you stop and think about, if you wanted to build some sort of knowledge base somehow from text, then all these advantages already give you advantages to building a knowledge base. So for coverage, let's say we already know kind of the things we want to put into our knowledge base because we've got a Wikipedia article out, and there are going to be quite a lot of them already. Then there are encyclopedic articles, it's relevant information, it's not like we have to feed in tons of text to get some sort of information out of it. We also have roughly the same amount of information per topic. Up to date, great, is collaboratively done, that's all awesome. And the meta structure already gives us a little bit of semantics that we wouldn't have in a normal text. And when I build the Wikipedia network now, we're going to make use of a few of these points. So there are 3 observations. The first one is that an article roughly corresponds to a concept or a thing in the world. So a thing of interest that is going to go into our knowledge base. So we know what the nodes are going to be in the network. As I said, 3.5 million. So to give you an example, I'm going a little network right here. So for example, we have a page on the Oxford Uni Computing Lab somewhere. We know that's going to go in. We've got Uni of Oxford somewhere. relationships between these things from the Wikipedia text. So the second observation that we use is that the hyperlinks you have roughly correspond to an occurrence of the concept. And what I mean by this is, let's have a look at the first sentence of the OECL. The OECL article. And it's the OECL, this would be marked as the name of the article too, is the computer science department. And computer science would be linked to the computer science page at Oxford University. Again, this would be linked to the critic page in England. So what these hyperlinks give us is, compared to, let's say, completely plain text without any hyperlinks, is that we actually know that this thing refers to computer science as it is described in the article Computer Science. So we actually kind of know what this is talking about. And it's really important for words that are ambiguous. So, I mean, this is not an amazing example, but let's say you only have the word Oxford somewhere. It could refer to the city or it could refer to the university. And people will have marked it and hyperlinked it to the equating concept, and you know which one it's talking about. Obviously, it's more interesting if you've got something like that. You don't know if it's riverbank or financial institution. But this is really an important aspect. This is ambiguation, and you know that this is information on that concept. So we're going to move on to the third observation, which is that we get quite a lot of interesting information about the relations of these things out of the text. So we know that this is a department at Oxford. So we've established a connection between the article OECL and the article Oxford, for example. And these are linguistically accessible to some extent. So text gives us some sort of relations. And here again we've got an advantage of using Wikipedia instead of plain text. Which is that it's more likely that this is actually relevant information if it's like, say, in the first paragraph of Wikipedia than if you just randomly found some text which contained OUCL. So I'm going to leave this a little bit as a black box of how the linguistic tools work, if you don't mind, and I'm just going to give you the resulting network of that sentence. So the first part is the OECL is the computer science department. So quite a few different types of nodes. So the red ones are those that refer to articles. The department here, and so we've got is, relation here, and we've got a specification here, which is linked to computer science. It's a department at Oxford Uni. So here we get different type of relation that is at. We can see that this is a direction. Yeah. So all the relations, you know what the subject of the object is. And we also have in England somewhere. Now the nice thing is that we can gather this information and actually establish a knowledge base by merging every occurrence that we have or every information on this concept into that node. So next thing that we'll do probably is look at the first sentence of Uni of Oxford, and that's going to contain also the information that this is a university. quite a lot of these. Quite interesting, really. Then again, if we go...
So the easy relationship is something standard, but you have just defined a way to extract it from the sentence.
No, it's really just how it is stated in the text. So the text actually says, like it says here, the OECL is the computer science department. There are a few other constructs that would also give is, but it's really just linguistically based. So you really just get the stuff.
But you have a standard set of these kind of relations. They have
No.
these and no.
No, they're directly, they come from the text.
So whatever was in the text happened to be in the text. Will go there.
Pretty much. So I mean, there's a point, I'm going to get to that in a second, of why it's important to use specific linguistic tools to actually get interesting stuff out of it. But for now, it's really quite close to the text. No. So if you have something like the student handed in his work to the tutor, then you would have like a handed in relation.
How do you tell the department it's not a page? Not a Wikipedia?
Oh, but just because there is no link.
Because so you don't go and look to see is there a
No.
Wikipedia?
We use the information that the users have already given us. One reason for it is that, let's say, well, we can go off and automatically put some links into Wikipedia. But again, that would be automatic and it wouldn't be of as high quality as it is from human users. So, yeah, in the next step you could try and see whether it's still good if you do it automatically, but for now I'm just going to stick to whatever users have told us. Okay, so first sentence of university would give you that it's an institution of higher education and research, and research. Got another one here. Which grants academic degrees. So, just to get back to why is it important to use these linguistic tools. If you just have a look at the sentence, here we got rid of all these like stop words or the whatever. We've extracted the most important information. We know which thing attaches to what, right? That in England modifies Oxford University, for example. So it has already done quite a lot of stuff for us in noticing the subjects, noticing the objects, etc. In particular, if you look at this sentence, and the original sentence is, a university is an institution of higher education and research. And it has split this "and" up into two relations that we'll work with. Just one second. And it has also resolved the subclause, which grants academic degrees, and also attached it here. Yeah.
Can this protocol handle multiple subjects or like multiple, where something's, where one sentence modifies another sentence, like where it's everything's spread apart, multiple sentences, or can it just analyze one sentence at a time?
Well, so I use a plugin tool, and you can do something like that. So you can set it to analyze a discourse rather than a sentence. So it could analyze something like the OECL is the computer blah 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 it, and then it would see that it is OECL. I'm actually not using it because it doesn't do that much, so the gain is relatively small right now because it's really hard. So the co-reference resolution I said in the beginning is a really hard task. So I've decided to just go sentence by sentence because it slows down the tool to do otherwise. But theoretically you can do it, and it's also set up to do something like that. It would be nice if we could do that. Right. A second argument for using the linguistic tools, and not just like going with a plain text, is that See, there are many ways of expressing exactly the same thing in language. So instead of the progress of the student, you can say the student's progress, right? And it means the same thing. And to a limited extent, the tool is able to map these to the same structure. So it kind of unifies or standardizes the stuff that you get out of it. So let's move on to the actual resource that we built. So for our first experiment, and this is extendable, we only took all first sentences of all Wikipedia articles. But that gives you 2.2 million article notes. The red guy is over there. It's 2.2 and not 3.5 because you've got quite a lot of disambiguation pages, which you wouldn't really consider to be a description of a concept. And also because as you go along the way of the tools that we use, there will be some noise which we filter out because we want to have as good as information as possible. And the number of other nodes here, like the things you see on the paths describing the relations, altogether we've got 34 million nodes. If you maybe roughly estimate that a relation maybe goes over 2 to 3 nodes, this corresponds to maybe 10 million paths that you already automatically get. And the whole thing, including all pre-processing, linguistic parsing, building of the network, etc., saving of the network, took 48 hours. So now if you think back to WordNet of 150,000 concepts in 10 years, this is quite a different dimension. Now, obviously, it's not as precise as a structure like WordNet would be, right? I mean, I haven't evaluated the quality of the relations yet, but obviously not all of them are really going to give you something very fundamental about the relation between the concepts, but it's already quite a good step, and, well, maybe we can kind of compensate quality with size.
How many different types of relations do you get out of this?
Well, as it comes from the linguistic analysis, it's not so much that we have a fixed set of relationships. So this comes from the verb brand, for example. So every verb would really give you a different relationship. But this is also actually a good thing about it, as you saw from the example of machine translation, that you need to play on as a relation and not just this thing. So in general, it's a good thing to have more relations in your network than less, because it gives you more information. Sorry.
So I'm thinking that a lot of the Wikipedia articles are historical in nature. Do you have any way that can, using your linguistic tools, sort of cut down the number of ways of representing temporal connectors, like since, or in, or between?
Well, some of it... Okay, so the linguistic tools that we use here, it first does a syntactic analysis, and then it puts it into a logical form. So this thing actually translates everything into first order logic, more or less, right? So it's going to give you, there exists a concept that is a department, and there is an event that is an is, etc. And that can't really deal with temporal relations too much, or spatial. So it will probably, so if you have something like this happened in 1958, it would just give you an in 1958 relation.
Okay, so not established in 1200 and something, or since 1200 and something, which would be roughly similar?
No, not at that point. The thing is, if you actually, this is exactly the problem. If you start wanting to deal with all of these things, you would run it, even if you just started looking at all the first sentences and everything that you would want to consider, you suddenly get into solving semantic representations of computation linguistics, which is really good.
I'm wondering about the way attributes are attached to these things. Now, what level of specificity do you attach to it? So every time we have an is, it's between a more specific and a more generic thing. So for univox of is a universal, Now the attribute in England, in that situation you've attached it to the more specific one because it's the University of Oxford that's in England rather than a general university. But then when it comes to university is an institution, so the university is the specific one and the institution is the generic one. You still attach those attributes which are specific to universities, you attach them to the generic box. And I'm wondering what's the kind of general rule that determines which boxes you make the attributes in.
Okay, so this is decided by the parser. So it's not my decision how it's done. And it's usually the syntactic structure. And quite often it is ambiguous, so it's going to make a decision as to what is more likely to be the right one of attachment.
And what does right mean then?
Good question. I mean, and in some cases it's really obvious, in some cases you could think that you could go either way, and humans would even decide differently. Where so does now England specify UCL or University of Oxford? Kind of depends on how it's said in the sentence.
And is it easy to update these networks? I mean, every time somebody asks a new article, you know what to place it.
Yeah. So what you can basically, as long as you can load the network into the memory, then feed in some more text and add it to the network, and
So
then
this
that's it.
48 hours is only the first time. And then
Yeah. So this is as I said, the first sentences of all articles, but you can do it. Basically, you can do it with any sentence that contains either two links, because well, otherwise you don't really gain anything from the knowledge base, or a sentence that contains the name of the article with it. So if you have the article on dog, then basically every occurrence of dog in the article is going to be an occurrence of that article too. So you can increase the amount of occurrences.
So if you read your articles get corrected,
Yeah.
presumably, you have to push it over if you want to.
That is true, but the good thing is, I mean, even if you do this, let's say, every 2 weeks, it's not a very big time to do it.
Can you have some quality measure of this thing that you have? Because I mean, having too many things doesn't necessarily good. And for example, what I was thinking before is that having too many relationships is not that meaningful as having a few. Like is for me is a very important relationship, compared to grant.
That's true, that's true.
And I could do the same thing, for example, with the Google pages, right? And links to Google pages. You could get a hugely bigger graph. So how would you evaluate how good is this?
So the evaluation, well, you can do two things. You can do an internal and an external evaluation. I do external evaluation, which means I plug it into a task, and if that one does better or as good as the manual thing, then I'm happy. Right. So or if you do it internally, you would maybe have a few poor students sitting there checking 500 relations and looking whether it's good or not. But obviously this is a hard way to evaluate. So in these cases it's always best to evaluate it with an application.
And can you find contradictions with this kind of measure of knowledge? Like there are two articles that contradict each other.
Well, I thought about this in the beginning, because I thought at the very, very beginning of my DPhil, I thought I could build ontologies from this. I think the information that you get is probably not quite precise enough to really do reasoning on it and say, well, we've got this relation here and there's not somewhere else, so this is contradictory. Maybe you can get some ideas from it, but I wouldn't go as far as really trying to...
Well, at least maybe it would tell you something about the code. Right, so there was a measure of the wood in this network.
Yeah.
And maybe if you look there, you realize that there's something wrong with the structure.
Yeah, that's true. Come up with a test like this. Yeah. Okay. Next thing, I'm going to show you how to use this thing. So is it clear how this looks? And the task I've chosen to work on is semantic relatedness. And that's probably going to ring a bell from this talk. So semantic relatedness is actually quite a simple thing to grasp. 3 word pairs, and I ask you to judge how similar the 2 words in the word pair are, and give it a score out of 10. So the first one is car, gasoline. And the second one is territory in kilometer. And the last one is Professor Cucumber. I actually didn't think of these examples. They are out of the evaluation set that is used. So Professor and Cucumber. You'll probably be happy to know that this got a very, very related score.
In which context? Professor was making a salad using cucumber.
Yeah, so I think it's probably really clear to you that, or you would all say that car and gasoline is really strongly related. Territory in kilometers, somewhere in the middle, and then Professor Cucumber is not related at all. So this task is really interesting for several reasons. First is, obviously, it's got lots of applications in computational linguistics, and if you can do that, you can do other interesting things and plug it in. I'm going to not go into that. Secondly, it's quite a complex task if you think about what sort of knowledge you put in into judging this. And we all have this intuition about it, and it's, well, minus some differences whether you would give it a 5 or a 4. And we kind of make very similar judgments on this. But if you just give it a moment and think about why you chose these to be really related. So it's probably because, well, you definitely need gasoline to operate a car, right? There's no way you can not do it. And also, this hardly ever, the concept never occurs really without the car anywhere near, right?
Because you can put one in the other.
You put one into the other, so you can actually come up with really quite a lot of relations of why. Okay, so second one, territory and kilometer. You're probably at some sort of score, because you can measure the territory in kilometers, the size of it. But it's not super related. It's not like you can not talk about kilometer without mentioning territory. And Professor Cucumber, well, hopefully just isn't any relation. Anyway. So because of this complex information that you use for it, it's quite difficult. And also knowledge bases like WordNet really have a problem with it. So think about car and gasoline and how it would be in the taxonomy that we just had in the very beginning. So we'd have car somewhere here, and it's going to be some sort of vehicle, and it's going to be some sort of, I don't know, one entity, object, whatever, right? You go up the tree. Then if you try to find gasoline, you probably have to go somewhere down chemical substance, blah, 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 and then you come to gasoline. So any kind of thing that you would do on this knowledge base in order to find out whether they're related or not wouldn't really work, because you might want to think of something like, so how many steps do I need to take through that tree in order to get to the other one? And that would be really, really quite a lot in here. But it's because this relation is needed for whatever is missing in that database. So, let's do some semantic relatedness on here. Pen and plus. Oh yeah. So, the first student of Wikipedia uses a concept called distributional hypothesis. That's really well known in computational linguistics. I've been talked about it before. So it basically simply means that if two words have a similar meaning or are somehow related, they're going to co-occur with the same words. So if you, let's say you got all the sentences that contain car apart, all the sentences that contain gasoline, and you have a look at the words that are in these sentences, then you'll find that the overlap is really big between them. So vehicle would probably come up in both of them, or maybe gas station, or whatever. While if you look at all sentences that contain professor and all sentences that contain cucumber, you'll find a very, very low overlap of, the content words that co-occur with it. So that's basically already it. Now the thing that I need to do is to get from this distribution of hypothesis to one that you can do on networks. And the general idea is just to say, well, if two nodes are really related in a network, then they're going to be related to the same things around them. So we measure the similarity of the things that are surrounding. Let's pick that one. So we've got our territory article node somewhere, right? And that's going to be connected to some other article node, or maybe indirectly connected to something very interesting over there, right? And those are going to be connected in it. So you can just imagine like the local network that you get around that territory node. So probably if you then look at the one of kilometer, you're going to find quite a lot of overlap of that local network. That's general idea. How much kilometer? Oh, perfect. Right. So let's look a little bit at how the details of this work. But before we can measure the relatedness, actually we've got to do a pre-step, and that's a mapping. And what I mean by that is that you've got to actually find the article in Wikipedia or in the Wikipedia network that corresponds to car or gasoline or whichever. Now this sounds really easy, but it's not necessary. For those, it's pretty straightforward, right? But it's not always the case. So, for example, there will be concepts that don't exist in Wikipedia, or that don't quite exist in the sense that you want. So if you type in arrival, for example, there's no article on arrival as the general concept of getting to B somewhere, but it's going to have arrival, the film of the year 1980, etc., or arrival, the music album, or whatever you can think of. Right? So it might not always you might not always have them that way. And also there might be just different options. So you hit a disambiguation page and you've got to find the one that you want. Again, in most cases, that's quite easy to do for us, but first of all, for the computer, it's going to be exactly the same, right? And you maybe have a list of 20 things and it's going to pick it. Then there's also the problem of, and specific in that task, that varies which one we want to map it to. So let's say you look at Jaguar and cat. You're probably going to give this quite a high score of relatedness because you're going to think of Jaguar, the big cat, right? Then I give you Jaguar and car, and you're going to think of the brand. So we have to take this into account that we can't just go and say, oh, right, this maps to X, and it's always going to be the same. We actually have to look at which pair we're looking at in order to get the right score. Because obviously, let's say the computer mixed these two up, you would get really low scores in both. But you want really high scores. So we do this actually quite intuitively, quite simply. For 2 steps. The first thing is to find all candidates. So say roughly for now we look at a disambiguation page and pick all of those that are on there. Works a little bit differently, but that's basically it. And then we have the Jaguar cat somewhere in the Wikipedia network, and we've got Jaguar car or brand. And good thing is, because we've used these hyperlinks when we built the network, is that we've divided up the information that we got in the text. So we know exactly when there was a Jaguar in the text, which one it's talking about. And this is where it comes in to be really, really cool. And we've got cat somewhere here. Then basically, what you do here is you usually always pick the sense that is closest to the other, so where they're most related. So we can just have a look in the network, how close they are in the network. And I found that a simple measure was actually really good. So if we just look at all the paths of maximally linked to, by that I mean there's only one hop over another article node. I'm not talking about the little ones a bit. So there will probably be quite a few that say this is going to be animal, zoo, I don't know. But there are going to be very, very few going over here. And plus or minus a little bit of weighting, I just looked at the number of edges that you get out of this. And then it really disambiguated it already quite well. So this has improved it over a certain baseline. It also overcorrects a few, but it actually does quite a lot very well. So that's the first step that you do. Now we know which local networks to look at. So the second step is, you might have guessed, is a vector space model. So the reason why I do a vector space model is like I just said we have to compare the local networks around it, and it's really nice if you map it onto something that is really well known and that you can measure similarities with quite easily. So we're going to build a vector space model. So the local context, local network effects. It's going to go into a vector V effects. And that one's going to have, as dimensions, the nodes around it. This value is a measure of importance, and I'm going to get to that in a second. So then once we've got the vector, we measure relatedness by the cosine similarity. So as we had that in the previous talk, we just have a look at basically the angle between the two vectors, and if they're really close, then we say it's really related, the contexts are really similar. If they're far apart, they're not. That's all there is to it. Now we've got to find a way of judging which local context we actually want, right? How far we want to go, and we also want to have some values of this vector that are meaningful, a measure of importance. And for that we use something that is called spreading activation. Now, spreading activation originally comes from neuroscience, and it's the idea that if you've got a network of neurons in your brain and you stimulate one, it sends off this stimulation to the surrounding ones. If they get stimulated enough, they start firing as well, so you get like some sort of activation going on around it. And that's exactly what we're going to do in the network, pretending that these are our neurons. So basically, what we do is we put some activation into the territory node. We let the activation spread. If the activation in some other node goes over a certain threshold, it also starts spreading along the links. The signal attenuates, so it only, if it has 10 units of activation but 100 links, not a lot of activation is going over the links. So it does usually start within maybe 2 or 3 hops in most cases. And the nice thing is that, so you can see like the surrounding nodes lighting up and being activated. And you also get a measure of importance to that concept by the amount of activation they get. So this is really important, let's say, to distinguish a node that is connected over lots and lots and lots of relations, or one that only has one, or also nodes that are quite far away and that don't actually have any connection to that node, but it's really, really strongly connected over other things. And spreading activation just kind of does it quite nicely for us without us having to count paths and do something, because it, you know, it combines a lot of complex things already together.
So there are some weights needed for thresholds and so on. Are they preset, or do you have some learning?
I don't have learning. It's just like a tuning, and hopefully
There's no
it's getting
feedback in your neural.
No. But it would be nice, maybe another PhD thesis. Look at the details. There's actually quite a lot of parameters in this whole thing, so depending on which node, how much you want to spread it, etc. So I'm hoping to get around too much tweaking here. Okay, so that's it already. So now we've got our vector of x, so this is territory, for example. And the entry is going to be simply the amount of activation that an article node in that local network gets when x is activated. Make sense? Okay. We can just choose, basically, with mi being a node, and the type is article. And most of them, I mean, most millions of nodes are going to be 0. I mean, maybe activate 2,000-3,000 of them. So that takes me to the end of the overview of semantic relatedness. I'm going to give like a 2-minute outlook of the other application that I'm going to look at. And that is the relation of nouns to compounds. So say you've got apple pie. You want to have a description of the relation between apple and pie, right? There are different things that you could think of, right? How to paraphrase it. So, for example, pie made out of apples. Or apple and pie, etc. And there are evaluation sets where humans have been asked to come up with paraphrases, and that they've been ranked according to how many people came up with the same thing. So you can try and come up with, like, train your system or get your system to come up with the same paraphrases, hopefully with the same ranking, and be really good. So hopefully this is going to happen with my approach. And this is really an application that is going to go into the relations. So far with the semantic relatedness, we haven't actually used the name of the relations or the name of the paths. We've just kind of seen them as a black box with a link, really. So really, very roughly, what I'm going to do is do the same mapping, find pie, find apple, and then look at all paths of some sort of length, maybe filter it out to structures. Well, let's see how much of this we actually get. And this probably also asks you a question of how to evaluate a system. This would be an external evaluation of it that actually goes into the relations to evaluate. Yeah, that's it.
Questions? There's only one page on Wikipedia with the word professor and cucumber in close proximity. And the sentence is, Professor Ochanomizu is the head of the Ministry of Science. He has a very large cucumber-shaped nose. Apparently his most sensitive area. But interestingly, that's 2 sentences with a pronoun in the second, referencing the professor in the first.
Well, as you see there, that's the only relation, and this approach really works quite well.
Yes?
Yeah, so one quite annoying thing in this semantic relatedness that came out of this example is that it does not satisfy the triangular inequality. So car is not related to a cat at all, even though they're both related very much to jaguars. right?
But they are related to different Jaguars, right?
Yes, but still they are connected through in your graph through the Jaguar, like even farther away, right?
But
So do you have a Jaguar in your graph that it's connected somehow to the two Jaguars?
No.
No, at all.
No.
So, but then you were using that to choose what is the correct Jaguar. And
yeah,
that's a separate step.
Yeah, what I do is I keep track of all the actual occurrences. So let's say you look at Oxford Uni. It's just an example I know. And then the name of the article is Oxford University, or I don't know which one it is. But you find variations. You find University of Oxford. Oxford, you know, you find different types of labels that you actually have in the text, and I just keep track of all of them, so I can actually look at the actual word that has occurred in the text, and that's how I get to the Canada. Does that make sense?
Yeah, and this is independent from this graph.
No, it's in the graph. It's just like, I mean, these nodes I have a little bit more information in them apart from the article name. I mean, you can also go and just look at all. So I think in the actual graph you've got something like Jaguar. That's the cat. This is the actual name of the article, and then Jaguar. Brand or car or whatever. So you could kind of, one candidate retrieval would be to just look at all article names that contain the word Jaguar, but it's a little bit better to actually look at the words that have been tagged as that because it gives you more information. Yeah.
When you're doing the cosine similarity, these are 2.2 million size vectors, is that correct?
But they're sparse.
They're
so
sparse?
Because what we do is this spreading activation, and it only like looks at the local context. So there will be maybe 5,000, 10,000 nodes that get activated, and then the rest of them you can just forget about them because it's going to be zero.
Are they pre-computed, or do you compute them as needed and activate? You compute them as needed.
More general question. So in your case, you create this graph of knowledge from Wikipedia, which is public information. So, but there are some private components that have private information or use of knowledge. So, for instance, Google page, in the case of Google, they have all information, all the emails or queries in Google, Facebook, YouTube, calendar, whatever. So they certainly also use some kind of techniques because they have all the advertisements, email, or Google queries. They also, the priority is also defined in terms of your profile. Do you know if they use this kind of techniques or what kind of things they use?
Well, I'm not an expert in that. I really don't know. I mean, the actual
page. If you
page
have all the information, you can create something similar on this, right? If you have all those databases.
Yeah, in general, yeah. I mean, but this is kind of just network theory, right? So, I mean, Google PageRank algorithm just works on hyperlink structure. So if you have a web page that has a link to a different web page, there will be a link, and then the PageRank algorithm that gives you the ranking.
But they also have a parameter that is basically your profile, right? Because if Costas does a query and I do the same query, maybe we get a different order in the result, right? Just because he queries more often certain words than I do. I don't want to make any example here.
Yeah, I'm really not sure how exactly that works, I'm afraid.
Your first example was this with the translation. So have you done this for a second language, and could you then try to map these two graphs on top of each other to see if you could do translation by statistical means?
Probably. The nice thing about this PhD topic is that there are lots and lots and lots of applications that you can think of. Yeah, I mean, if you wanted to do it in Wikipedia, the nice thing when people have used this structure is you know how an article is linked to its counterpart in the other language very often. So what you could do theoretically is build a corresponding network for German and then have some sort of mapping between the corresponding articles and do something with it. But that gets quite complex and I wouldn't
Okay, we reconvene in 10 minutes.
Thank you very much.